Hi, everyone. So we're very happy to have Ralph Blumenhagen from Max Planck Institute for Physics in Munich, who is joining us virtually and will tell us about nullifying cobordism in quantum gravity. Ralph, please.
Yeah, first of all, I would like to thank you and Urs for inviting me to this conference. Unfortunately, I couldn't make it to Abu Dhabi this time. So I listened to some of the talks yesterday and also the day before, and I realized that I might be an exotic member here because my background is rather from physics and not so much mathematics. But nevertheless, in an attempt to understand this recent paper by McNamara and Waffa, so we entered into the theory of cobordism. And so maybe it's also useful for you, I think, to maybe get a physicist point of view on these things. And in particular, here we are not so much talking about applications to topological quantum field theory, but rather to quantum gravity. So what I would like to report on, as I said, is based on the work, or at least this triggered our work. This was the work by McNamara and Waffa, and we did a couple of papers together with a postdoc, Niccolò Crobiuri from Munich, and then two PhD students, Christian Kneisel and Adriana Macridou, and a master student, Chuying Wang. Okay, so maybe here for this audience, let me just summarize what we are now concerned about in the field of string phenomenology and string model building. So in the past, we were thinking that, and you have maybe heard about it, that string theory can realize many quantum field theories, low energy effective actions, and these were called the landscape, and this was even proposed as maybe a solution to the cosmological constant problem and so on. But on the other hand, it was also clear, I think from the very beginning, that it's not that all for itself consistent quantum field theories in 4 dimensions can admit a UV completion in a theory of quantum gravity, in particular string theory. So string theory were giving you much more constraints on these 4-dimensional effective field theories. And in a more recent endeavor, the aim is to delineate, so to say, here the boundary between the landscape and the swampland. The swampland are those theories which cannot be realized in quantum gravity, and to maybe give you some quantitative or fine quantitative, simple quantitative relations that helps you to distinguish which theories are in the landscape and which are for sure in the swampland. And this program sort of is called the Swampland program. Okay, so one of these swampland conjectures usually be formulated in the form of conjectures because mathematically we don't have a proof for them, but we have arguments for them. And these arguments are mostly based on quasi-classical arguments, say, based on systems that we think we understand, like black hole evaporation process and so on. And of course, with our experience from string theory. And one of these conjectures is the conjecture that there should be no global symmetries in quantum gravity, which is definitely opposed to what we are used to in quantum field theories. So here I don't want to repeat all these arguments. So there are some arguments about black hole remnants. If you throw in particles carrying these global symmetries, since they are not gauged, you cannot detect them from the outside. And if the black hole evaporates, you are left with, in principle, infinitely many remnants. And this is thought to be a problem. Similarly, more quantitatively in string theory, so we know that global symmetries on the 2-dimensional world sheet, where we have a conformal field theory for on-shell configurations, they lead to gauge theories in the 10-dimensional target space. So that's not clear how could we get global symmetry. So any global symmetry you might detect in 10 dimensions can at best be accidental and is very likely to be broken by some other effects you have just forgotten, like a non-perturbative effect. Okay, so if we are in a situation where we have reasons to believe that there should be global symmetries, it should better be nullified. So in the sense, and the physical mechanisms to do that is a gauging of the symmetry, which is shown here. So let's say here this is for continuous symmetry in d dimensions. This means that, say we have a conserved current here, that on the left-hand side, we introduce a gauge field, a higher form gauge field, such that the equations of motion for this gauge field, or the Bianchi identity, so to say, couple has this current on the right-hand side. So first of all, it's then trivial that the derivative of it's vanishing, but you also introduce new degrees of freedom, namely the gauge fields. And that's the way, for instance, for this black hole argument, that you can detect now. So these particles now carry flux lines. So if you throw them in, there's still the flux lines are still leading out, so to say. So you can detect the charge of the black hole by Gauss' law. Okay, that's one way. And the second way is more straightforward in some sense. So this is just that the symmetry is actually broken by some other effect. And this means that the derivative of the current is not vanishing anymore. So there is if the current is an n form, so there is something on the right-hand side of this equation, which is an n+1 form in that case. So these are the two physical mechanisms. And okay, this was just for global symmetries. And I mean, the contents, the main message of this paper from 2019 by McNamara Waffer was that if you have a non-trivial cobordism group in your theory, then this means that this creates a global symmetry for you. So first of all, it computes a charge. So these cobordism groups, these geometric cobordism groups, for instance, are usually z-valued or z2 valued or something of that kind. And so this gives you a global charge. And then they had arguments how to build even gravitational solitons from them, which then behaves very similar to what we are used to for branes. But we also know that there are global symmetries induced. And so there's a strong belief, and they have arguments that a non-trivial cobordism group creates for you a global charge. So we have learned that there should not be any global symmetry. So as a consequence, they conjectured that the cobordism groups eventually needs to be nullified. And so if you start, I don't have to tell you, so mathematically, you are probably mostly interested in cobordism groups which are not vanishing. Yeah, so often that is the case. So if you choose a certain tangential structure, like spin manifolds or spin C manifolds or string structure, then not all of these cobordism groups are certainly vanishing in any dimension. So you often have non-vanishing ones. So what you need to do eventually is to refine or extend your structure, to put more structure in the cobordism group, which you might call geometric structure, as far as I understood from the talks yesterday. So that when you now compute the cobordism group with this extended structure, you will eventually find zero. And eventually all of these have to be zero. So but then after this sort of new idea entering the story, there was a body of literature on this work. Of course, I understand that there was also previous work also by the organizers of this conference. But now sort of this put a different perspective on it, this I would still say, because they related these cobordisms now to global symmetries. And in string theory or physics, we know a lot about how to treat symmetries. And we could now think about cobordisms, as being inducing global symmetries. And this gives, I think, a new perspective on that. Okay, I think here I don't have to define what the cobordism is, but maybe just to give you also some physics point of view. So so if you have chosen a certain tangential structure, so you say that two manifolds, say of dimension n, are cobordant if they exist a one-dimensional higher manifold W here, such that the boundary is the disjoint union of the two things that you want to connect. So if you now think you have a non-vanishing, say, cobordism group, or you have some cobordism here, dimensional n, dimension n manifolds. So if we now think about string theory being a higher dimension theory in d = 10 dimensions, so we can think now of this as a compactification, and then we end up with an effective theory in d - n dimensions. And you can think of the cobordism, because it has one dimension higher, W, as a domain wall, separating these two manifolds M and N, or these two string backgrounds M and N. And then the cobordism conjecture physically tells you that topologically, all allowed quantum gravity configurations are connected to nothing via finite energy no baseballs, because eventually the cobordism group has to vanish. Okay, so I mean, the definition of, because we need that later, of cobordisms can of course be refined. So you can also define cobordism groups with a certain tangential structure in a background manifold X. So now you have not just only manifolds, but you have also maps of all the objects M, N, and W on a fixed background X. And of course, everything now has to be transported consistently from M to N. Okay, so now a bit more information on the breaking of symmetry and to refine what our intuition from global symmetries tells us here. So if, say, a symmetry is broken, so we have this n+1 form here on the right-hand side, now we can think, or McNamara-Waffer thought of this n+1 form as being the Poincaré dual of some new objects of the respective dimensions such that it fixes. So this means that this new object here, this defect they call it, is of codimension 1 in the uncompactified dimension, in the d-n dimensions. Okay, so what you need to see now in cobordism theory, so to say, why such a configuration can trivialize your former non-vanishing cobordism group is that you extend your structure by now also including these defects, so some point-like or singular objects here. And so even if you had, so say you had a manifold M where before there was no W existing such that it connects to 0, but now with this extra defect, so to say, this defect you can think of as closing off now this cobordism W such that it trivializes M. So that's the way geometrically they think about it. So, and then you would expect that there exists a map from your former cobordism group with tangential structure Xi to the one where you include the defect, just by forgetting the defect. And then, so those objects that are killed, so which are in the kernel of this map, so are mapped to 0 here, these are the ones that we are interested in, those global symmetries are broken, and so they are eventually killed. And this is what we want to have. No? And this should be considered as a step-by-step process where you start with something non-zero, then you add defects. We have to find defects that can nullify the cobordism group, and this then you need to include in your structure. This is how they think about it. Similar for gauging. Here, a priori, you don't need any defects, but you can extend it, and I need that in a moment. So here, what you need to do is by gauging now a current Jn, so you need to introduce a gauge field. So you certainly should include this gauge field, this higher form gauge field, also into the structure of your tangential structure of your manifold. And this is, I think, what you would call a geometric structure now. And okay, so then this is automatically trivialized. And so, but here, as we'll see in a moment, in theory, also allows you to do a bit more. So you here also could allow for defects of the correct dimension to also appear here in this Bianchi identity on the right-hand side. And here the defects are not of codimension 1, as you can see from the degree here, but of codimension 0 in the uncompactified dimensions. So you can think of these as branes. Right? And then again, you would expect to have a map from your refined cobordism group or extended cobordism group to the old one where you see the global charges, and then the elements that are in the image here and are not mapped to 0. So these are the ones that are killed in the full theory. So those symmetries have been broken, and only this one here remains, but this is gauged. Okay, so I think you know an example of that, or we all know an example of that. This is the string cobordism groups. So where you have a trivialization of the first Poincaré class over 2. So usually you look at geometric configurations or spin manifolds also having P1 equals 0. And then you classify all the cobordisms, but it's a matter of fact. So this can be thought of as coming from a Bianchi entity of this type here. And then you also need to include this higher form, so this 2 form, B2, into the structure of your cobordism group. Okay, so some of the results are known, but I think, to be honest, in principle, in general, I haven't seen yet, but maybe this might be my ignorance, really ways to compute such cobordism groups, say, in full generality. In particular, including all these defects in the theory. Okay, so this is not what we want to do. I mean, this is probably work more for the mathematicians. So here, as physicists, so we were just trying to understand that better and was seeking answers to the general question. So how these nice ideas are actually realized in string theory. And moreover, so what are the codimension zero defects that in principle we could also include in our gauging procedure. And we'll see, and this is known, that in string theory, these are actually there. And moreover, as we have seen, the breaking gives rise to codimension one defects. So are these known in string theory, or are these all known in string theory? And this was more or less one of the main question of this paper by McNamara, to point out which defects could do this breaking. So we will have now, we will see in a moment or later, that there's also some very much related issue here. When you look at certain solutions in string theory that were known for a long time, which were not understood, but with this new perspective of cobordism and thinking of defects, they could now be understood much better. I will tell you at the end about that. So this goes under the name of dynamical cobordisms. Okay, and there are more. So these are still simple and questions that we could attack, but there are much more involved questions, that one would like to understand. So first of all, how far can one develop this picture without relying on string theory, actually? So just starting with this theory of global symmetries, gauging and breaking, can we develop sort of a bottom-up approach that leads us to what kind of structure we eventually have, where all cobordism groups are vanishing? And is this directly leading to string theory? So is string theory the only solution, so to say, or at least the topological parts of string theory? Is this the only possible solution to this program, or are there more? And moreover, more mathematically, so we had these two maps for gauging and for breaking. So I think from the mathematical point of view, so this should be part of a more general theory, so part of a spectral sequence probably, where you also now include in your structure these defects. So at least I don't know how this is properly working in mathematics and how these things should be properly defined. So this is also more a question for the mathematicians, I think. Okay, so then let me report. I'll summarize very briefly the contents here of this first paper together with Niccolò Grigori. So here we were looking more closely at the gauging procedure in string theory. So what are these cobordisms mean, actually? I mean, so we have done a lot of work on string phenomenology, string model building, D-brain constructions. So of course you have the feeling that if somebody comes along and says, so here's a new structure, you should have seen it before. So it should have been there for the full time, but maybe we didn't call it a cobordism, okay? And this is indeed the case. So in string theory, so what is happening here? So in general, we have P-form gauge fields, Ramon forms, for instance, satisfying certain Bianchi identities. And in general, they are of the following form. So you have the derivative of this field strength is a sum over so-called localized sources of these things, so charged objects under this Ramon form. This would be D-branes in particular. And there are also, in particular from the Chern-Simons terms in the D-brane action, there are also terms that are topological invariants of your background manifold. So other currents, like here, something like trace R, wedge R, trace R. So these things do appear here. Okay, so these are the objects on the right-hand side. So if we have Ramon forms, so these localized branes are known to be described, or at least the charges can be computed via K-theory. So this is what Witten told us many years ago. Okay, so we see here a relation which apparently connects on the right-hand side currents that are classified by K-theory and other geometric things. So the natural guess, as you can imagine, is that these other things, this is where the cobordism enter, the geometric cobordism groups enter. Okay, so let me just tell you something about K-theory. So in type 2b, so type 2b D-branes are classified by these complex K-theory groups. And we have Bott periodicity, as you know, so all the even ones are equal to Z and the odd ones are vanishing. And this gives the charge of a BPSD brane in 10 minus 2n. With 10 minus 2n Wald volume. So this is the map from K theory to branes. And in type 1, the non-oriented type 1 theory, here the branes are classified by the orthogonal K theory groups that are in Z-valued or Z2 valued. There's a periodicity mod 8 in this case. And this also includes not only the BPS branes in type 1, but in type 1 we have this special situation that there are also stable non-BPS branes. They're not preserved supersymmetry, and these are precisely classified by these two valued things. So a single brane is stable, but this tells you that if you put two branes on top of each other, you create a tachyon and the whole thing will decay. Okay, so what about the geometric contributions? Well, just look at an example. Of course, we have many more examples in the paper. We developed step by step, but here I just give you, so to say, from the backwards point of view, so immediately simple examples which suggest the general result. So let's look at F theory or type 2B or antifolds. And the initial story is to compactify type 2B down to 8 dimensions, and then you need to introduce 7 branes into the theory. And then there is a Bianchi identity for one form field strength. Where on the right-hand side, you have the sources for the 7 branes, and in addition, a geometric piece, which you can write as the first Chern class of the manifold. So actually the on-shell F theory setting, M is actually a P1 equal to P1. So you can write it as the first Chern class over 2 times a coefficient, and this coefficient turns out to be minus 24 in that case. So this is nothing else than F theory compactified on a elliptically fibered K3 manifold with base P1. Okay, so this is maybe not too suggesting, but it tells you what the form of these geometric contributions is. Maybe more interesting is maybe if you look at the similar story, if you compactify F theory on a Calabi-Yau fourfold, again elliptically fibered, so there's a complex base in that case. Here, B3. And then in this tadpole, or this is also called a tadpole cancellation condition, by the way. So then in the Bianchi identity, now you have the 3 branes as the D brane sources. And in general, you will here have the Euler characteristic of your Calabi-Yau fourfold, but you can show that if it's elliptically fibered, you can express it just in terms of these 2 topological invariants on your base manifold. So and again, I've written it that this is really the Todd class, the third Todd class here, and this is an additional topological invariant. Again, the coefficients are fixed here, just fixed from the F theory. But if you now look at these expressions here, this will maybe remind you that there's a relation to spin C cobordism groups. So for spin C structure, the non-vanishing cobordism groups, the first ones are known. So here they are. So again, you have not periodicity, but everything is mod 2, and you have just factors of Z. So, but you have a proliferance of factors with respect, say, to the corresponding K theory groups, but to classify the D branes, you have a proliferance of factors here. And if you now look, this second line here gives you a basis for this lattice here. And if you now look at the cobordism invariants, they are also known for these cases, you find the following list. And you see precisely that the cobordism invariants are those things that appeared here as the geometric contributions. In particular, here, I mean, this is just a complex manifold. You could wonder why is C3 not appearing here, no? The third Chern class, and it isn't. So if you evaluate the Euler characteristic of the fourfold, you get this on the nose. So, and indeed, this, from the cobordism point of view, of course, spin C invariants, cobordism invariants, don't have a C3. I mean, because in general, the manifold is not complex, it's just spin C. So, so they are generated by C1 of the line bundle that you always have there, and then the Pontryagin classes, actually. Okay, so we have the claim that the geometric pieces in these Bianchi identities, these are described by the cobordism invariants, in this case of omega n spin C with structure spin C. Okay, so and what actually happens, so what these global symmetries are from the string theory perspective is rather, so if you have this gauging, but now if you ungauge them, then all of these extra terms here would appear as single charges, so to say, they would not be gauged anymore, so they would appear as global charges, and the K-theory global charges you would, the D-brane charges you would compute by evaluating K-theory groups, and these contributions, these numbers, so these are just numbers, no? These charges you would compute by computing Cobordism invariants. Okay, so that's the picture that we have. Good. For type 1, it's very similar. There's a similar relation in this case between the orthogonal K-theory groups and now the spin cobordisms. What we cannot fix, so what we still take here from string theory, are these coefficients and the gauging. And it would be nice maybe to have also for these sort of a bottom-up approach to fix them just by, say, mathematical consistency and not by doing really full quantum gravity that you know already. So this we don't know yet. Okay, so if you want to write in one Bianchi identity objects from K-theory and cobordism, there should better be a relation between the two, because you need sort of to have very similar factors, at least, in your cobordism groups and K-theory groups. Otherwise, this wouldn't make any sense. And indeed, when we, naive physicists, they were looking up a bit in the mathematical literature, we found such relation, and this goes under the name that I don't need to tell you probably, Batia-Bott-Shapiro map. So this tells you that there exists a ring homomorphism precisely between the spin C cobordism groups and the complex K-theory groups, and similarly between the spin cobordism groups and the KO groups. And when restricted to a fixed grade, these maps are the Todd class that we have seen already for spin C, and essentially the A-roof genus with some prefactors and so the number of spinors you can define on these manifolds. Okay, and this picture, I mean this homomorphism can also be made an isomorphism. So there's a famous theorem by Hopkins and Hovey that precisely does that, and so this also allows you to do the whole thing, and also for background manifolds X, and then you have a map between essentially an isomorphism between spin and KO groups and spin C cobordism and just K theory groups. Okay, so there is this relation. And so this is what is the underlying mathematical reason for why you can gauge in string theory cobordism charges and K-theory charges at the same time. Okay, so now we have this more. The second question we wanted to ask is to get a better understanding of what these objects actually are, where you have also a background manifold X. So how would we compute them? And what is their string theoretic relevance? So in some sense, at least, we were moving back from our initial goal of trivializing our cobordism group. So we are moving one step back by even introducing now a background configuration X. And this also leads to, if we have non-vanishing cobordism groups here, we will get even more groups, so to say, more factors in these cobordism groups. But nevertheless, we would like to see, so now we are compactifying, so we can think of this as now literally compactifying string theory on a fixed background and classifying, for instance, by K minus Nx, all D-branes, say, in the uncompactified directions. This is what these things classify. And from K-theory, we know already that this is following essentially the rules of dimensional reduction. And so this, at least as long as all the maps, so as no extra issues arise, I would say, but extra issues could arise. In particular, it's known that if you have a brane wrapped on a certain manifold, they could be subject to so-called Fried-Witten anomalies. For instance, they should better wrap a spin. So they should wrap a spin manifold. If your manifold is not spin, you need to turn on an extra gauge field on your brain, making it spin C. Yeah. Or you could also have some H free-form flux through the brain, and then this brain would also not be allowed. So some of the brains might not be there, that you would naively expect from dimensional reduction might not be there. And in addition, I mean, if you now wrap brains on various cycles, of course, you have, again, a lattice of charges. So then what could be, if you take two brains wrapped on different cycles, I mean, there could be a new decay channel. Tachyons could appear that makes the system to decay. Yeah, so this wouldn't appear in the corresponding K-theory groups then. So mathematically, the way to compute these K-theory groups with the background X is via the Atiyah-Hülsenburg spectral sequence. And we went a bit into that direction. And there we see, or you could see, that the Fried-Witten anomalies are related to some non-trivial maps in your spectral sequence at some point. And these new decay channels, we think that they are related to this extension problem that you have at the end of the Atiyah-Hülsenburg spectral sequence. Yeah, so this extension is often not unique and sometimes not so easy to solve. And we think that this is related to these new tachyon decay channels physically. Okay, so we did just a very modest thing for mathematicians probably. So we choose very simple backgrounds, but backgrounds that are familiar from string theory, like spheres or tori or K3 or Calabi-Yau. And then we were running through the spectral sequence and just to see what we get. And for these simple things, we get a very nice or very simple result that is completely consistent with the expectation from dimensional reduction. So it tells you that the K minus N group with its background X is a direct sum of the K-theory groups of the point, and then there's a coefficient here in front, or the number of these factors is given precisely by the Betti number of a certain cycle in the Calabi-Yau. So this literally tells you that brains in lower dimensions are coming from brains in 10 dimensions wrapped on certain cycles in your Calabi-Yau or in your manifold. And now we would like to see whether for spin C, there should be a similar pattern. If it holds in this case, then there should be, again, because we want this gauging that we have that relates K-theory and spin C cobordism invariance. This should be consistent under dimensional reduction, so they should behave in the same way. Yeah? And indeed, I mean, the spin C cobordisms, as you know, are also computed by Atiyah-Hülsenburg spectral sequence, and you find a very similar result. Yeah? So, and indeed, these groups here, you can see that they classify from the perspective of global symmetries. First, I mean, we expect this dimensional reduction relation because we expect them for global symmetries to hold. No? So this is, again, physics intuition, and this should be reflected by the mathematics. So these groups here then classify, so for fixed N, classifies all D minus N minus 1 form global symmetries in the non-compact dimensions. And this is completely consistent with dimensional reduction of gauging, tadpoles and breaking, at least in the simple cases. But in the more complicated cases, so where you have non-trivial maps, say, where you have Fried-Witten anomalies, again, if you lose a factor here, you should also lose it here. So there should, again, be also non-trivial maps when you compute the corresponding spin C cobordism groups. This is our expectation. Okay, so this is more or less the more mathematical part from my point of view. And so now let's talk about breaking. Okay, so as I said, so this analysis of when you have non-trivial cobordism, spin or spin C, what kind of object you might introduce in string theory to break it. This was analyzed partially by McNamara and Waffer. So where we contributed is in a slightly different setting. So this intuition we have now from Cobordism, this introduction of codimension 1 defects and so on, this was reminiscent of something that was pointed out by the group in Madrid around Angel Uranga, that something we had really in for on-shell solutions in string theory. So we had in string theory, we encountered a simple effective field theory for string theory, but having now this dilaton here, this dilaton tadpole, so a non-trivial exponential potential, say, for a scalar field, not necessarily the dilaton. So often you encounter effective theories like that, like for instance in the so-called Tsukimoto model. This is a non-supersymmetric orientifold of type 2b, or in massive type 2a, where you turn on in type 2a a constant Ramond zero flux. You also encounter a tadpole like that. And then the question is, so what is the back reaction? What's the solution, the on-shell, not off-shell now, on-shell solution to such equations of motion? First of all, you find that there's no solution preserving d-dimensional Poincare symmetry because of this running. But there are solutions where you have one non-trivial direction and still preserve d-1 dimensional Poincare symmetry. So here's the ansatz for the metric. So you introduce these warp factors that now appear on this single non-trivial longitudinal direction. Okay, and now you can go into the equations of motion and try to find solutions for, in principle, arbitrary. This is what we did in this recent paper, I should mention. So for arbitrary value of this coefficient b, and what you find is that there are solutions that are of finite size in this y direction. So they are of finite size, and they have singularities at the end of these finite sizes, at the boundaries. And precisely at these singularities, the dilatons of the scalar field and the curvature diverges, but with a very specific scaling law. So the distance to the finite distance to this wall scales in the following, scales in an exponential way with a canonically normalized dilaton, like here. And there's a coefficient delta appearing here. And the same coefficient also appears in the scaling of the divergent curvature when you come close to such a boundary. And moreover, the type, what we found in that paper is that the type of the solution very much depends on whether this parameter that you have there is larger, or smaller, or equal to a certain critical value that in d dimension has this value. And so when you now look at the boundaries that you have in all these solutions and you sort of classify them and you see what kind of objects, of singular objects you get. Okay, so the question was, so we have these singularities now here in these solutions. So that's usually a disaster for string theory. We don't want to have singularities. So, and this is now a bit reminiscent of the situation when you have a non-vanishing cobordism group. Yeah? So you need to find now objects that you can sort of say put as sources at these singularities that cap off your solution or close off your solution. So there should be new objects in the theory that resolve in some sense these singularities. So this is now the new idea which is motivated by cobordisms. And okay, so first of all, if we now look at these solutions that we have and the end of the world, we call it end of the world branes, the behavior you find, you can compute for all cases. So L and R means left and right, and minus and plus means whether the dilaton goes to minus infinity or plus infinity at that boundary. And here is the coefficient delta that we find. So you have these various regimes and you look at what delta is, but you realize that delta is always larger or equal than essentially this critical value. So even if B, this coefficient, is smaller than B critical, delta will always be critical. Yeah. So there seems to be, in some sense, two objects now. I mean, one as a new brane which has delta B critical. I'm neglecting now the square root of 2 just to make my wording easy. Or at least in these two cases here, we also have end of the world branes where delta is larger than B critical and precisely up to the factor of square root of 2 equal to B. So the question is, so there should be these new objects. Can we find also solutions? I mean, again, on-shell solutions for these, in this case now, 8 branes. They are codimension 1 as the defects in the breaking of cobordisms. So they are of codimension 1. And they should preserve, of course, 9-dimensional Poincare symmetry as the former bulk solution was. They should feature the same singularity close to their core as we have detected. And as a matter of fact, because they are these end-of-the-world branes where space really ends, they should be non-isotropic in the transverse direction. And so, again, we made an ansatz for such a, first of all, for a neutral brane, so which only, again, has a coupling, certain coupling to the dilaton, but now it's codimension 1. Here's a delta function. And then we implemented the boundary. So first of all, we've wrote down the bulk solution. Then we implemented the boundary conditions that we were expecting. So for instance, for y smaller than 0, there should be nothing. So the metric should go to 0, and GS, the string coupling, should go to 0. For y larger, there should be a non-trivial solution to the bulk equation of motion. And for where the brane is, we should have the corresponding jump conditions. And indeed, when you do all that, you find that with this ansatz, consistency requires you that this coefficient that we have now here in this ansatz for the brane has to have this very specific value, which is, as you can see, up to a factor of 1/2 closely related to be critical. And you get precisely, okay, and the tension of this object needs to be negative to satisfy the boundary condition. And this is precisely the scaling behavior of these ETV branes with the value delta being be critical. So this we have found. So this is a neutral brane. So what kind of object is that? So if you now do the whole thing in 10 dimensions, when we are related to string theory, really, so the string brane action now in string frame of that thing turns out that this coefficient here, that the exponential of the dilaton is, in one case we have two signs here, e to the minus 3 phi and e to the minus 3 over 2 phi. So this is neither e to the minus phi or e to the minus 2 phi. These are the brane tensions that are usually known that appear in string theory. So this is no known brane tension. So this is supposed to be a new object in string theory. Of course, we cannot say whether it's stable or unstable, but just for closing off, so to say, this the singular solution, it's good. Yeah. So it points. This is very much reminiscent, really, of this cobordism picture, where you also, if you have a non-trivial cobordism group, you want to break it, you also introduce new objects, new defects in your theory. Here, we are not just topological; we're really talking about on-shell solutions. So. Okay, so there can be now generalizations. So we are still left with the question, so what is with those end-of-the-world branes that have delta larger than B critical? And we, in the paper, we precisely find also these branes. These are, for these, you have to also introduce, you also have to introduce a non-trivial Raman field, and sorry, a higher form field. Yeah, and so these objects will be charged branes. And again, they precisely exist for B larger than B critical. So there's really a one-to-one correspondence between objects we need to close off with singularities and objects that we can construct as solution of with the right codimension type brane. Yeah, and the story can also be generalized to more codimensions. So there's a dual model, T-dual model, which is called the Blumenhagen font model, which we discussed here in this very paper from 2000, and this can also be fixed, or can also be made compatible with all these ideas. Okay, so this brings me to the end. So what we formulated here is sort of a dynamical cobordism conjecture, saying that for a solution of an effective supergravity theory featuring a singularity at finite spacetime distance, that's a special. Consistency with quantum gravity requires the existence of an explicit solution for the end-of-the-world brane that closes off the spacetime. So there should be a defect to make everything nice and compatible. Okay, so conclusions. So what we have seen is that the gauging of K-theory and cobordism charges, first of all, in string theory, they come together, and they lead to tadpole cancellation conditions that have precisely the form known from oriented-forward and F-theory constructions. Here, K-theory provides the brane charges, and the cobordisms the geometric contributions to the tadpoles. And turning off the gauge field again, so makes this really the global charges that are computed. Moreover, the dynamical cobordism can provide a gravity or supergravity description of these ETV branes. That's also nice. There are still many open questions, I think. I don't even know where to start. So first of all, what we mainly discussed is type 2b and type 1. So we don't have the clear picture yet for type 2a branes and tadpoles. And from the mathematic points of view, so the next step, the next logical step, which might be difficult, is to find ways to explicitly compute cobordism groups with this extended geometric structure where you also put higher form fields in your structure, in particular also these localized defects. So this must be some joint thing of K-theory and cobordism in some sense. Then we are just computing numbers here, charges. So far we have no bottom-up approach to determine the relative coefficients that seem to appear in the string theory gaugings, at least. So are there constraints? Certainly there must, just to think this is rate to anomaly cancellation. But how to make this really precise, we don't know. Then we have these new objects for which we now have gravity, supergravity descriptions, these end-of-the-world branes that are not just D-branes because they have not the right tension. So you might ask, is there also a two-dimensional CFT description maybe for at least for some of these objects, like a defect in CFT? And moreover, is there a unique bottom-up result for the final structure unique in quantum gravity to trivialize all cobordism groups? So these are the questions that appear here, which mathematically might be difficult to answer, but you are the expert, so to say. So yeah, I think this brings me to the end. Thank you very much. So sorry for being over time by 5 minutes.
Thank you very much, Ralph. Any questions for Ralph? So, Ralph, is the idea that these cobordism groups house anomalies, and that's why they need to be nullified? Is that the idea?
I think it's not anomalies in this sense. I know that cobordism groups have been applied by Fried and others to the theory of anomalies, and there might be a relation that I don't know. But here, the aspect is really that cobordism groups generate global symmetries. And as such, we have reason in quantum gravity to believe that they should better be nullified because there should not be any global symmetries in quantum gravity.
Oh, I see. It's more about symmetries. I see.
It's more about symmetries, and it's more about really the application in quantum gravity. If you do other things with cobordism groups, a non-vanishing cobordism group might be just what you want.
Yes.
But here, the aim is actually to nullify them at the end and to refine your structure such, or to extend your structure such that this is possible.
Okay, sounds good. Thank you.
It's just terminal, just trying to understand, when you say cobordism groups generate symmetries, your talks, I got the sense that cobordism groups, detect symmetries as opposed to...
Yeah, it's not maybe good wording. So what cobordism, the cobordism groups that we all compute with geometric ones, with spin structure and so on, these just detect global charges.
Correct,
so the cobordism groups are related to global charges, that's all. Right. So you expect global symmetries to be there. So generating is not maybe the right word.
Right. So you're in some sense, the philosophy is if there is something to detect, then there should be something to detect. So you should get rid of that thing. Okay, I see what you're saying.
Yes.
Okay. Any other questions? Okay, if not, let's thank Ralph. Ralph again.
Yeah, thank you very much.
Nice. Thank you.
Thank you.
Thank you very much, Ralph.